Bismillahirrahmanirrahim. Today we are starting our uh, lecture on geometric progression, and in this progression we see that the common ratio between the two consecutive terms is always constant. So in this term we have first term is A, and the second term is the common ratio between the term is R. So in a geometric progression we move from A to AR, and then AR square, and then AR cube up till AR4, or finally ARn minus 1 to the nth term. So we will work on it. So the sum of geometric progression is given by this summation. Sn is equal to A 1 minus R power n upon 1 minus R. So we'll perform some this 11.4 in this session. So we have this 11.4. First questions: identify whether the sequence are geometric or not. If they are geometric, write down the common ratio and 8 term. So we have solved this, and this ratio 2 4 here 1 2 2 4 2 2 6 4. Oh no, it's not. So similarly for the others one. Second, the first term in the geometric progression is A, the common ratio R. Write down the expression in terms of A and R, the 9th term and the 20th term. We will obtain this. The third term of a geometric progression is this. The sixth term is this. Find the common ratio on the first term. So we'll solve this these three problems. So starting from the first, we see that common ratio. Here ratio is this geometric. No, this is not, because the ratio is not common. Not 2. Here we don't have. For geometric progression it has to be 8 instead of 6. This should be 8. Here this we have minus 4. So this is geometric progression. Here we have 1 by 3. So this is geometric progression. So no, this is not, with different values. So for E, the question number 2 is here An is equal to An Rn minus 1, A9 is equal to Arn minus 1, 9 minus 1 is AR. For 20th term we have this one. A3 is given as 108, A6 is given as minus 32, and A3 is equal to AR square, A6 is equal to AR5, R3 cube is equal to A6 upon A3. The ratio of this is given as 8 upon 27. So this is minus 22 upon 3, ratio cube on both sides, taking cube on both sides. We have got this value from A3 to AR, and then we got A value. And from the fourth problem, this was our requirement, the first term that we have obtained. Now move back to the first term and common ratio as obtained. The first term of a geometric progression is 75 and the third term is 27. Find the two possible values of the fourth term. First term and third term is given. The first term and third term is given. From this we have obtained this R, this two possibilities. Common ratio, if R is equal to 3 by 5, then we have this value 16.2, and for if R is minus 3 upon 5, then we have this. So there are two possibilities. For question number 5, yes, Let's move to question number 7. The sum of second and third term in a geometric progression is this. The sum of second and third term in geometric progression is this. The second term is 9 less than the first term. Given all that terms in the progressions are positive, given that all the terms in the progressions are positive, find the first term. Here we have second term is given as this, third term is given as this. The first term is S1, second term is A plus AR squares, S3 is this one. So the difference of S3 and S1 is this 30. A minus AR is given as 9. S3 is given as this. So from this S3 minus A we have 30. S3 minus S1 is given as 30. So we'll place it here, and from this we have A is equal to this one. So in place of A, this term may be placed here, and we have to find the value of R by solving this. So as a result, we have solved the value of R as 2/3 and -5. So that all the ratios are positive. So we will take here R is equal to 2/3. So for R is equal to 2/3. So we have A is equal to 1 minus R is equal to 9. So A is equal to 27. So we have obtained this value 27 by solving it by using these relations. A to AR, A3, S1, S2, S3, and by solving this was given as a input solution information. From this information we have obtained these things, and finally as a result of this we have obtained this. This is a very, very important question, and it may be asked in final examination. Similarly for question number 8, 9, we have this kind of progression. The first term, which is the first term to exceed 500,000. So an is this, and an minus 1 is this. So as a result this, so AR is equal to AR upon A is equal to 2. The ratio is 2. So ARN minus 1. So we place it here, A in place of A and place of R, and we get this value for n minus 2 we have. So this is 2 raised to power 2, it becomes n minus 3. So taking log on both sides, we take this value, and finally we obtain this, n is equal to this. So n is 22. So for problem number 10, we have solved it here, and we got this. So n is greater than, this means n is equal to 19. N is greater than this value, so n is 19. Should be greater than 19 for the particular solution. So similarly for 12 problem, we obtained is 14. Let's solve question number 14. The third term of a geometric progression is 9 times the first term. The third term of a geometric progression, the third term A3 is 9 times the first term. So A3 is equal to 9A. The sum of the first 4 term is K times the first term, means KA. Find the possible value of K. Okay. So this is A3 is equal to 9 times A1. This is the given information, and S4 is equal to K times A1. These two informations are given. By using these two information, we can solve A3 is equal to AR cube, and AR cube is basically the AR cube, and A ratio is 9. So R square is equal to 9, means R is equal to plus minus 3. So if R is equal to 3, then we can substitute it here to get this K value and equate it, and if R is minus 3, then we equate it like this. So the possible value of K is minus 20 and plus 40. So question number 16. A geometric progression has first term A, common ratio R, and sum to n term is Sn. Show that S3n minus S2n divided by Sn is equal to R power 2n. So we'll solve this. We have to show this. We know that S3n means here the power is 3n. For S2n, here the power of n is 2n, and Sn is this. So by taking the left hand side, this is this 3n, 2n divided by Sn, we have this. So here we have S3n and Sn, S2n, Sn, and we have solved it, and we got this value. So from here to this, we have further solved it to obtain this, and then R2n, so which is the right hand side. This has been proved. Question number 17 is a challenging one. One, 1, 3, 1, 3, 9, 1, 9, 27, 127, 81, 1 over 81. Show that the sum of the first two n terms of this sequence is 1 upon 2, 3 power n minus 3, 1 minus n plus 2. So this problem has to be solved. Question number 17, we have this 1, 1, 3, 9. So we have AR square, AR cube. So this is 1 over 3, and this 3 is 1 over 9. So we can take it out in two different terms by taking this 1, 3, 9, 27, and then 1 over 3, 1 over 9, 1 over 27, 1 over 81. The two different series. So we have this taken this, the two different series. First one is this one, the second one is this one, and we add it up, and we have obtained from this series we have geometric sum of geometric progression this. From this series we have sum of geometric progression this, and by addition of this we have obtained like this. This was our requirement, so we have proved it, and now we will proceed to the exercise 11.5 where we will solve some infinite geometric series. The first one is 3 plus 1, 1 upon 3, 1 over 9. So we have to find the infinite sum of geometric series. For this geometric series, the sum is given as this 1 a upon 1 minus r, and the r is between minus 1 to 1. If this condition satisfied, then we can solve the sum of infinite progression as 1 over 1 minus r. So for this one we have this s is equal to 3, 1 minus 1 over 3. So we have solved it. B, C, similarly for other one. So for second problem we have a and r as 10 over this. So we have to find the infinite geometric progression. We have obtained this is 50. For this 300 to this one, we have a as this, ar 3 as minus 12 upon 5. So ar 3a. So the ratio of ar cube is given as this, and from this we have this 1 over 5. So in place of 1 over 5 we have this. So the sum of infinite series for this progression is 250. For this we have this progression. So for this is 0.80, this is 0.2, this is 0.82, this. So we have this ratio is constant. So infinite progressions, we can write it in place of a we have 1, r is 0.8 square, so it becomes 2.778. The fifth one we have 0.4 double dash. It means this decimal numbers are repeating, so we can write it as a this value s is equal to a upon 1 minus r. Here r is this value. So r is 0.01. So in placing this we have obtained sum of infinite geometric progression as 14 upon 33. For problem number 6 we have the solutions. Let's go move to the problem number 9. The first three terms of a geometric progression is this, this and this. This is the first term, second term and third term. All the terms in the progressions are positive. Find the value of k and sum to infinity. So we have to find this value of k using a geometric progressions. So for a, 1 is equal to 175, a2 is k, and a3 is 63. So this is the given information and all the terms are positive. The value of k is, we have to find the value of k. So s is equal to, and similarly the sum of infinite series. So from this two information, a2 and a1 we have a and a3 and a2 we have a constant ratio. So as a result, this is AR, this is A, and by using this relationship we have here we have K, and this is 175, this is 63, this is K. So by this cross multiplications we have this value, and from this we have plus minus 105. For all terms are positive, so the geometric progression, so the value of k is plus 105. So from this 175, our ratio of common ratio is 0.6. So in placing this a and r 0.6, we will get this sum of infinite series as 437.5. We can solve problem number 10, and for problem number 11, the first three terms of a geometric progression are k plus 5, k and k minus 12 respectively. Find the value of k and sum to infinity. So these are the three continuous geometric progressions. The first three terms, this is the first term, this is the second one, and the last one. Find the value of k and sum to infinity. So we have to solve problem number 11, which is given here. This is the first term, second term. This. The value of k, we have to find the value of k. A1 is equal to k plus 15. A2 is equal to k, which is AR is equal to k. A3 is equal to k minus 12, which is AR power n is equal to this. The ratio of this A2 and A1 and A3 and A2 is R. So in place of A2 we will write k. In place of A1 we have k plus 15, and in place of k A2 we have k and this. So we can formulate this as this expression. Finally the k is 60. So k is 60 and a is equal to k plus 15 is the first term, is as given. So as a result the a is obtained. A is 75. So in place of a we write 75, and from this r value including we have obtained 375. For question number 12 we have solved it here, and question number 13. Now move to the question number 14. The first term of a geometric progression is 1, and the second term is 2 sine x, where x is between minus pi by 2 to plus pi by 2. Find the set values of x for which this progression is convergent. So this is problem number 14. So here A1 is given as 1 and A2 is given as 2 sine x, and x is between minus pi by 2 to plus by 2. So set of x for convergence. So we have to find the set of x which is convergent. So A1, that is A, is equal to 1, and A2 is equal to AR is equal to 2 sine x. So R is given as A2 divided by A1 is equal to 2 sine x. So sine x is equal to R by 2. So x is given as sine inverse R by 2. So A3 is given as AR2, and AR is given as 2 sine x. R is given as 2 sine x. So this becomes 4 sine square x. So 4 sine square x is less than 1 for convergent. So if this is less than 1, then it becomes convergent. So sine square x is equal to 1 by 4. So sine square is equal to plus minus half. So if sine inverse half plus half minus half, we have this pi by 6 and pi by 4. So if x is less than pi by 6 and pi by minus pi by 6 to pi by 6, then it will be a convergent series. So this is important question. This may be asked in final examination. So this is very important. Now question number 15 is also solved here, and now we will continue from 11.6 in the next session.